Piloting a glider is all about air currents and gravity doing the work. Suppose this glider's getting ready to land. It's descending at a constant rate of 400 feet per minute. In t minutes, the glider descends 400 t feet. If you started tracking its altitude at 2,400 feet, you could relate its altitude in feet above the ground to time using this equation. H is the altitude in feet, and t is the time in minutes after you started tracking it. Graph the altitude on the y-axis against the variable for time on the x-axis, and you get a straight line. Here's the equation again, with the expression on the right having the term with the variable first. It's in the form ax plus b. That expression is a simple example of a polynomial. A polynomial is a mathematical expression that can be written using only operations of addition, subtraction, and multiplication applied to numbers and variables. In this linear equation, the expression on the right is made up of two smaller expressions, its terms. The variable t is a factor of the first term one time, so it can be written with an exponent of 1. It has a coefficient of negative 400. The second term, 2,400, is a constant term and has degree 0 since it has no variable. The whole expression has degree 1, the greatest degree of any of its terms. When a function is based on a degree 1 polynomial, its graph is always a line. Here's an equation for the height of a diver falling freely. T is the time since he started, and h sub 0 represents his initial height at time 0. Falling from 33 feet, the diver, after t seconds, will have a height of negative 16 t squared plus 33. A single variable expression like this one, with the variable squared as part of its highest degree term, is a quadratic polynomial. This term has two factors in it that are variable. Here, it's 2 t's, so it has degree 2. The coefficient of the squared variable is negative 16, and the constant, a term with degree 0, is the initial height, 33 feet. Now, the graph of height versus time is not linear, but is a special kind of curve, a parabola. The graph of any quadratic function of one variable, a degree 2 function, is always parabolic. Graphs of relationships represented by higher degree polynomials could have even more complex curvature. Let's see how polynomial expressions and functions can give you a new perspective on the world around you. This team of Rocketeers has high hopes for their latest fiberglass creation. It's a 1/3 scale replica of a World War II German V-2 rocket.
3, 2, 1, launch!
Suppose that in 6 seconds, the rocket runs out of fuel as it reaches about 3,200 feet. It's going at about 320 feet per second up. That's about 218 miles per hour. Say it continues on a trajectory influenced only by its motion and the force of gravity. We'll ignore air resistance. Its altitude at any time in feet, t seconds after it runs out of fuel, could be expressed by a quadratic expression, a polynomial with degree 2. Here's its graph. In this equation, the negative 32 is the acceleration downward due to gravity in feet per second squared. Dividing by 2 results in a coefficient of negative 16. It's used because the average velocity during the fall is negative 16 times t. 320 is the velocity in feet per second upwards at time 0. That is, at the moment the rocket ran out of fuel. 3,200 is the height of the rocket in feet at time 0. Let's change the scale of the graph so we can look at the contribution of each of the terms to this function. Here's the part of the function contributed by the first term. It's a polynomial with only one term, the second degree, or quadratic term. It represents how much the rocket would fall from the starting point due to gravity if it weren't going up. The second term is this one. Its graph is a straight line through the origin. It represents how much the rocket would go up from the starting point if it kept going up at its initial velocity. It's a polynomial with one first-degree term, that is, with the variable raised to the first power. The third term is constant. It's the altitude at burnout, and it represents the point where the rocket would hover if it weren't moving up or down. It's a polynomial function of degree 0. It's like the variable is raised to the 0 power, since anything to the 0 power is defined as 1. To get the graph of the entire polynomial function with all the terms, add all the displacements from the x-axis. First add the displacement of the 320t line to that of the 3200 line. Then add the displacement of the negative 16t squared parabola. That gives you the sum of the influences of all the terms for the final parabola of the function. The graph of a polynomial function can often be analyzed using the separate graphs of its terms to show the separate contributions of each, just as it takes all the contributions of the team to launch a rocket. What do a precious sparkling diamond and the graphite in a pencil have in common? They are both composed of the fundamental chemical element in living things, carbon. The carbon that formed diamonds got heated and pressed within the earth into the hardest natural substance in the world. The form of carbon you probably are more in touch with is one of the earth's softest natural minerals and a much less precious commodity, graphite. Blend it with clay, embed a filament of that in wood, and out pops a pencil. About 1,720,000 of them per day at this factory. The economics of production and sales can sometimes be shown by polynomials. We'll apply such a model to pencil production and sales. Suppose graphite were in short supply. As more pencils were produced, costs for materials, and therefore the cost of production per pencil, would increase. Suppose for any amount of pencil production in a day, it costs the factory $30,000. Those are its fixed costs. Beyond that, production of each pencil costs 5 cents, plus another 38 billionths times Q if Q pencils are produced. 38 billionths times Q is the increased cost per pencil due to the shortage of graphite. The cost of producing Q pencils, then, is represented by this expression, 30,000 plus Q times the cost for each pencil. The cost for each is 0.05 plus 38 billionths times Q. Expanding the expression results in this cost function for the whole production run. If the pencils sell for 18 cents each, then the total revenue, the money the company gets from the sales, can be represented as 0.18 times Q. Here's a graph of these functions. Notice that the revenue exceeds the cost for a range of values for Q between about 250,000 and a little over 3 million. That's when the company makes a profit. In fact, profit is the difference between revenue and cost. So the company's profit from selling Q items is this. Profit equals negative 30,000 plus 0.13 Q minus 38 billionths Q squared. The graph of this function is the difference between the heights of the revenue graph and the cost graph. This curve is above the horizontal axis in the range of values of Q, for which the company makes a profit. Elsewhere, it's a loss. But now it's easier to identify the number of pencils manufactured and sold that will make the company's profit the greatest. You can see that the company makes a maximum profit of $81,200 when it sells 1,720,000 a day. Whether a company is selling expensive jewelry one piece at a time or huge quantities of inexpensive pencils, it's all about making a profit. And polynomials can be a useful tool for projecting future earnings. Most drivers slow down when they see standing water in a roadway. But in the sport of swamp buggy racing, they speed right through it. In this sport, the standing water is the road. At this track in Florida, drivers race on a figure eight called the Mile O Mud, around hairpin turns and through two hazards called sippy holes, where the water's over 3 feet deep. You could model a swamp buggy's speed through a sippy hole. Suppose you had data on its speed at 3 points, one approaching a hole, one going through it, and a third after speeding up again. Suppose this is the data, plotted on a coordinate system. It shows the speeds at the various distances in feet from a reference point, 40 miles an hour at the start, 8 in the middle, at 50 feet, and 40 again at the end, at 100 feet. As long as each distance is paired with only one speed, you can always find a polynomial function that includes a given finite set of points like this. When you do that, you're using an important property of polynomial functions. The higher the degree of the polynomial, the more turning points, peaks or valleys it can have. Here, we can hit all the points with only one turning point. It's a valley, a minimum, with this quadratic polynomial function. But this doesn't model the swamp buggy slowing gradually. It's unrealistically abrupt at the ends. To model gradual slowing, we can add two more turning points, peaks, by making it this fourth-degree function. The maximum number of turning points a polynomial function can have is one less than its degree, the greatest exponent of the variable in the polynomial. For example, y equals x squared has only one turning point at 0, 0. A cubic polynomial, degree 3, can have up to 2 turning points. A fourth-degree polynomial can have 3, as we used for the swamp buggies. In general, an nth-degree polynomial can have up to n-1 turning points. You can get a polynomial to go up and down as many times as you want by choosing a high enough degree, and you can move the turning points around by choosing appropriate parameters. So you can make a polynomial curve go through any finite set of number pairs with different x values. You do that by combining terms of the appropriate degrees. It's not always appropriate to fit curves exactly. It depends on the data and the purpose. But with enough terms of high enough degrees, the curve can go up and down as much as you want, like the speed of a swerving swamp buggy.